Work is defined as the product of force and that force applied on an object, and that object will move, and the displacement it moves and multiplied by the force applied on the object is what is work. That is how work is defined. Work equals force dot product with the displacement of the object. Even though both the force factor and the displacements are factors, but since the dot product with two factors is a scalar, so work is a scalar. And let's see how work is used in our daily life. If you have watched TV or if you are interested in sports or some event you may heard of, an international event such as the Olympic event has many sports events in it, and from those sports events we can learn more about work. And some sports you may consider it may not look like sport since there is a force applied by the athletes that we cannot see from TV, and that sport is called weight lifting. And if you don't know what is that, I will show you below. Weightlifting is a sport that is the athletes will need to lift a weight. That weight may be some 50 to 60 or even 100 kilograms, depending on how strong you are. But normal people would be somewhere about 50 to 60 kilograms, and they compete in who is the strongest, and by lifting the more heavier weight, by holding the weight for a few seconds, that means you are able to handle that weight, and that weight is kind of quantifies how strong you are. And let's look at the physics behind weightlifting. And what athletes will need to do is only by lifting the weight, but that is not easy since the athlete needs to apply some force on the weight on both hands to lift the weight. But the weight is of course have mass, and any object that has mass will also have weight. This is not the weight we are lifting. That is the weight divided by physics as the mass of an object times the acceleration. In this case, the acceleration is the gravitational acceleration. So we can got this weight mg, and that would be located on the center of mass of the weight. And in order for the athlete to hold this weight in place, it will need to apply the force which is equal to the weight. That means the two forces applied by both hands by the athlete will need to equal to the weight of the weight he is lifting. And if the athlete can hold that weight, that means he can apply enough force on both hands to balance the weight of the weight he is lifting. Then he will qualify, and he will be competing in the next one, but to average. And in this case, we can look at is any work done by the athlete. You may think you of course needs to apply force in order to hold the weight in place, but according to our definition of work, that is, work is the force factor dot product with the displacement factor of the object. And we can look at what is the force factor. The force factor is these two factors, these two forces applied by the athlete, and those two forces applied by the athlete. And if we want to calculate the net force, we will need to add in the weight of the object. And if the athlete can hold the weight in place, then those forces will cancel out each other. That means the weight is not moving at all, so it has no motion, so the displacement is 0. And any force factor, though, that means these two force factors applied by the athletes, if we add those four factors together, we will get 2 times the individual force applied by each hand. Then we calculate the work as that force dot product with the motion, the displacement of the object. But since the object has not moved at all, so the displacement factor is 0, and anything multiplied dot product with 0 will be 0. So even though the athlete is applying a great force in order to hold the weight in place, but the physics still thinks the athlete didn't do any work. So that is some counterintuitive definition of physics. And there are, of course, more events in the Olympic. So let's look at another event. and this event is by throwing a disc by and the athlete will attach a string to throw a disc in order to throw that disc far away, further away. And how the athlete do that, how the athlete throw the disc away the furthest is by first they need to rotate on themselves. So they need to rotate on themselves and will also rotate the disc around. So this is the disc, and the hand applying a force, and the disc is going around in circle, and they keep rotating a few times before they eventually throw the disc out. But during the rotation of the disc is put into a circular motion. That means the centripetal force applied on the disc by the athletes and the velocity vector of the disc are perpendicular to each other, and the force vector is towards the center of the circle they are rotating. And the velocity vector is at the tangent of the circle. And if you remember, velocity is defined as the rate of change of displacement. So the velocity is defined as the rate of change of displacement, but since the displacement and the velocity are both vectors, so they must have the same direction. So the direction of the displacement must also be in the direction of velocity. So this is the displacement vector, which is at the tangent of the circle at the point which the centripetal force is applied on the object, on the disc. If we consider this motion of the disc circulating in motion, then we calculate its work done on the disc by the athlete, which is the dot product of the force vector and the displacement vector. And this force vector, since the force vector is perpendicular to the displacement vector, and the angle between the force vector and the displacement vector is 90 degrees. So we can write the work done as the force vector times the displacement magnitude and multiplied by the cosine of the angle between those two vectors. Since they are perpendicular to each other, so it is 90 degrees, and cosine 90 degrees is equal to 0. So this simplifies to force vectors times displacement magnitude multiplied by 0, and this is equals to, since that is 0, so work done must also be 0. So although the disk is rotating, but since the displacement factor and the force factor are perpendicular to each other, so the disk in circular motion has no work done on it. So also in this case, if the athlete is rotating around holding a disc, then physics still thinks no work done by the athlete. So, but we want to see sports, but sports usually need some physical work. So let's look at another example where there is actually physical work done. And for example, you are throwing a ball or something, and how you throw that ball, and the last moment you touch that ball, there is a force factor, final force factor applied on that ball. And since there is a force factor applied on the ball, and the instant the ball is released from your hand, the direction it will travel is in the direction of the force you apply at that moment, and that is the displacement factor, which is also in the direction of the force. So since in this case the displacement factor and the force factor are in the same direction as each other, so when you consider the work done on the ball, that is the force factor dot product with the displacement factor, and since both factors are in the same direction as each other, so we can just multiply by the magnitude and assume the direction of travel of the ball is positive, and so the force factor, both the force factor and the displacement factors are also positive, and two positive numbers multiplied together is also positive, so the work done on the ball is positive. In this case, the work done on the ball is not 0. So that in this case there is actually work done on the ball. So you can, in physics, you can say you done more work by throwing a ball than what a weightlifter can lift a 100 kilogram can do in the Olympics, but that is only the definition in physics and may not be the same interpretation when you use it in real life. So the physics define the work as the force vector dotted with the displacement vector, but that is still a little bit too abstract to understand. And if you think about how the energy has on the object has changed over time, you can consider it. For example, in this case, the energy of the ball is given by the kinetic energy on the ball, which is mv squared divided by 2, and m is the mass, v is the velocity of the ball. And of course the ball has velocities, so the kinetic energy is positive, but also the ball may have some gravitational potential energy since you are not throwing on the ground. And the gravitational potential energy is the mass times the gravitational constant acceleration by the height at which the ball is thrown. So the height is of course larger than 0 since the ground level is divided as 0. And here is the ground, which is at level 0, and the ball has some height from 0, so it is above the ground, so it is larger than 0. And the product is also larger than 0 since if you consider the mass and gravitational acceleration as positive, then all three variables are positive, so they must be larger than 0. And if you think about in this case, the ball has going from rest to accelerating to release from your hand. That means the initial kinetic energy is 0 as the ball is not moving from your hand when it is at rest, but the initial gravitational potential energy may be greater than 0 as the height may be lower. And if you think about what is the initial velocity, the mechanical energy, which is the sum of those two energy, and initially the only gravitational potential energy since the kinetic energy is 0, so if you add those two energies together, only left is the gravitational potential energy. But this is the initial, but find finally the ball has, when releasing from your hand, the ball has also kinetic energy as it is moving at some velocity. So the kinetic energy is not zero, and it also has some gravitational potential energy, and it is also not zero. So if you compare initial energy that the ball has to the final energy the ball has, you see there is the initial height, and this is the final velocity squared divided by 2 plus the final height. And assuming you are throwing at a higher height than initially the ball has, so the final height must be greater than the initial height. And so this term here, so the right turn here must be greater than the left turn. So the gravitational potential energy has increased, and the kinetic energy is not zero when it is released from your hand. So if you consider the initial kinetic energy is from 0 to the final kinetic energy, which is greater than 0, which is something greater than 0, that means the kinetic energy has increased when you are throwing the ball from rest. And when you consider the gravitational potential energy, the gravitational potential energy may be something greater than 0 initially to somewhere even higher as you are throwing the ball to a higher position, then release. So the gravitational potential energy has also increased. So the total energy or mechanical energy of the initial mechanical energy, which is equal to the initial kinetic energy plus the initial gravitational potential energy, and the final mechanical energy, which is equal to the final kinetic energy plus the final gravitational potential energy. If you compare those two mechanical energy, then you will find that the mechanical energy, which is, if you write this from our using the above, this is initial mechanical energy, and this is the final mechanical energy. And since you are throwing higher, so the bottom height must be greater than the top height. the final height must be greater than initial height. So if you compare these two terms, of course this term must be greater than this term, and this term must be greater than 0. So you will get the final mechanical energy must be greater than initial mechanical energy. That means the total energy of the ball has increased, and this is true if you consider that means the energy has going from a lower level to a higher level, and this implies the total energy of the system you are considering has changed. And when you consider a system that you consider its energy, and when the energy has changed, you will say the system has do some work. And if you see the following for example, you will see the work is positive. That means there is some work done on the system, and that means the energy of the system has increased, and that is how the work should be understood as the change in energy of the system. And if you consider the example from earlier, you see that to consider the circular motion. If you consider the ball from the initial somewhere traveling to here, and then to this position, and those are the two factors of work. And if you consider how the energy is changing in this system, that means the initial kinetic energy, which is mv squared over 2, and since the mass of the ball hasn't changed, then also you consider this is a uniform acceleration. That means the velocity vector in a circular motion has the magnitude of the velocity vector hasn't changed, as the centripetal acceleration only changed the direction of the velocity vector. So since the energy is a scalar, and scalar doesn't take into account the direction, so the kinetic energy of the ball is still the mass times velocity squared divided by 2. And this is the initial kinetic energy, and the final kinetic energy, since when the ball is going around the circle, the velocity hasn't changed, only the direction of the velocity has changed and the magnitude of velocity hasn't changed. So the final kinetic energy is still equal to the initial kinetic energy, as the magnitude of the velocity vector hasn't changed. So let's consider the gravitational potential energy. If the ball is circular around on a flat plane, as in this case, then the height at which the ball is traveling on shouldn't change. So the gravitational potential energy is mass times the gravitational acceleration times the height the ball is circling on. And since the height of the ball hasn't changed when traveling in circle, so the final gravitational potential energy also equals to the initial gravitational potential energy, as the height stays constant. And from here then you can add those two together to get the initial mechanical energy and the final mechanical energy, and see that they are equal to each other. That means the change in mechanical energy of the system is 0, and you see that the work is also 0, and that implies the mechanical energy, the change in total energy of the system is also 0. And so that is also true in this case, where the work implies change in the mechanical energy of the system. So if the change is positive, that means that if the work is positive, that means the change in energy is also positive. And when the work is negative, you could inverse all the factors and say positive, as when you replace positive by negative, you will see that means you will get a reflection, and you will calculate in this case negative. So everything is mirror to each other, and if the work is negative, that means the energy is decreasing. And in this case, if you consider there is also air friction when the ball is traveling through air, or dragging down the ball, the friction, air friction, or air resistance. And so usually the projectile of the ball is like a parabola, but when there is air friction, then you will see that the ball lands much earlier. So that means some energy of the ball must be transferred to the air as heat. So you will heat up the air along the way the ball traveling, and that means the work done on the ball by the air is negative, since air is slowing down the ball. So you will see the change in energy is decreasing since initially the ball has some energy, but finally it has less energy than initially the ball has. So the energy is decreasing. That means the work done also has to be negative. So those are how you should interpret work as the change in energy. If the work is positive, the energy is also positive. The energy is also increasing. But when the work is negative, then the energy change is decreasing. When the work is zero, the energy hasn't changed. So that is how you should see work as the change in energy of the system. And that is how work should be defined.